The first lecture for GNSS and the geosciences will be History of Geodesy and GNSS, or Global Navigation Satellite Systems. So beginning with early navigation was done without instruments, which required that the coast was always kept in view. Now this is during the daytime, which means that you're limited in your mapping. Now, navigation at nighttime was done relative to the stars and lighthouses, so you still had some sort of land-based component or some celestial component, which meant that your mapping was fairly limited. It was really limited, especially along the coast, and you kind of had these simplified maps. So here we have an example of a map that was produced using this approach about 450 BC, and you'll see that the coast is relatively simplified and that there's not a great amount of detail. Now, one improvement on that is Eratosthenes measured the circumference of the Earth using a Naaman principle and the equation where c, or circumference, equals 360 divided by theta, which is the angle formed between the well and the column. Multiply that value by s, which is the distance between 2 points that lie north and south of each other on the surface. So in this case, he used a column at Alexandria and a well at Syene and calculated their circumference of the Earth to be approximately 46,620 kilometers, which equates to about 25,000 miles. Now, this is really surprisingly accurate given that the modern accepted figure was 40,074 kilometers or 24,855 miles. So using simple geometric principles, we were able to calculate the circumference of the Earth about 200 BC. Now, the next improvement on this was by Hipparchus, and where he developed the nautical astrolabe about 200 BC. And what this allowed us to do is by sighting in a celestial object and measuring the angle between the line of sight from the observer to that celestial object and the horizon. So by measuring that angle, you were able to determine your latitude. Now, you were able to determine your latitude based on the elevation difference, or that measurement of that angle between the reference star over the horizon, and you compared that measurement to a predicted angle of the star at a reference location. That's also known as the ephemeris, which is a table of astronomical predictions. So you compared that measurement to the ephemeris, and you were able to calculate or determine your latitude, or your distance between the equator and the pole. Now, this really doesn't tell us anything about direction, so the next improvement was the compass was developed by Alexander Neccom in approximately 1190 AD. So what this allowed us to do then is, in addition to being able to determine our latitude, or distance between the equator and the poles, we are now able to determine what direction we were heading. And the advantage here is we were able to improve mapping to a great deal, especially along the coast. So you see as an example here of a map about 1100 AD where there's much greater coastal detail compared to the earlier map. And that's because we can determine more precisely what direction we are headed. So not only where we are latitudinally, but what direction you're headed. The next improvement is the development of the medieval portolan charts. Now, what these are is a series of crossing lines referenced to a compass rose. And at each port, you would have a compass rose, which would tell you directions to other ports. So here's an example of a chart. And at each individual port, you would see something similar to what's on the left here, which is a compass rose from the Catalan Atlas, where it would tell you the direction from that port, and by connecting the line from that port along that direction to another port, you were able to determine what heading you needed to take to get from one port to the other port. And this allowed us to further refine and expand actually our mapping capabilities. In addition, about this time, the understanding of, and mapping I should say, of the known world expanded greatly. So now that we have an idea about what the circumference of the Earth is and how to determine latitude, the next step is to determine longitude. So we already have our y coordinate essentially determined latitudinally. Now longitude, or our x coordinate, is much more problematic. So with the development of the sextant, we were able to solve this issue of latitude. And by measuring the lunar distance between the moon and another celestial object, we were able to calculate Greenwich Mean Time. And that you were able to calculate longitude. Now, this allowed us to map the Earth based on a series of latitude and longitude lines. So we were able to get more accurate maps like the one you see here. Now, longitude is based on the time at your location relative to reference time at a known location. So the problem with the sextant is you need some sense of visibility. So you need to be able to see the celestial objects. If you can't see them, or if you don't have that great of visibility, that is problematic. So in the late 18th century, John Harrison developed a clock which would work on board ships. Now, this works on a principle that you see here, a geometric principle, series of weights and counterweights. And the advantage of this is it's insensitive to the rocking of the ship. So regardless of whether or where it is on the ship, this clock will still calculate time accurately, and it doesn't have to be reset. So by measuring each hour difference, you're able to calculate where you are longitudinally, and each hour represents an eastward rotation of 15 degrees. And there were a series of refinements after this. So you see on the right, H1 is kind of the first generation, if you will, of John Harrison's clocks, all the way down to H4, which is a much more refined, more compact model that still works on the same principles. Now, radio communication at the turn of the century provided much more accurate time differences and allowed us to calculate our location over much greater distances. So with the development of the LORAN system, or long-range navigation system, a master transmitting station transmitted a signal, and then once that signal was received by a slave station, it would delay it by a millisecond and then retransmit that same signal back. And once the master station received that signal back, it was able to determine its location and the location of objects within that network. So this really improved our ability to communicate over and position objects over long ranges, long distances. There's a series of other terrestrial positioning systems which we won't get into very much, but I wanted to introduce them. There's the VHF, omnidirectional radio range, that's commonly known as VOR. There's the instrument landing system, the ILS, microwave landing system, MLS. And these are still in use today, particularly when it comes to air traffic control and on approach. So you can see here, there's a diagram using ILS and MLS for a runway approach. So you may see an array, such as the ones on the right, at different airports. So this course is going to focus on GNSS in the geosciences, or remember I said global navigation satellite systems in the geosciences. And the most common form of GNSS that you will hear about is GPS. Now, GPS stands for Global Positioning System, and its initial development, its primary purposes were A, to track soldier position, both friendly and enemy, and B, to serve as a weapons guidance system, more accurately positioning and targeting for those weapons. The GPS constellation, the satellite constellation, currently consists of at least 27 operational satellites. Generally speaking, there tends to be 31 or more satellites. However, the current constellation is known as an expandable 24, and it actually has 27 satellites or more. And we'll get into that more in a later lecture. These satellites orbit the Earth between 60 degrees north and 60 degrees south, which means you have your greatest coverage of the GPS system between those latitudes. Now, it orbits the Earth at an altitude of 20,200 kilometers, and that equates to 12,600 miles. And it's traveling, each satellite travels at 1.9 miles per second. So they're traveling really high, really fast, between 60 north and 60 south. Why a course in GPS? Why is it essential that you know this information and you know how the system works? Well, first and foremost, GPS is an easy and low-cost technology to determine your position in space. It's a relatively simple method. You can take a receiver out in the field and with relative ease determine your location on Earth. Now, the function of the actual GPS units and the GPS system as a whole is actually quite complex. And if you do not understand how the system operates and what may introduce error, it is difficult to understand how to design your survey. Ultimately, essentially, because of this ease and low-cost technology, it leads to a black box syndrome, which means it works, you don't know how it works, you don't know the quality of the data, you don't know what affects it. So the quality that you're getting back, you don't know. So the purpose of this course is to provide you with a foundation for how the GPS or GNSS systems as a whole, I should say, operate and how you can design a survey appropriately to minimize error. So here we have an example where GPS systems are used for construction surveying. So up at the top there, the yellow disc is actually the receiver. That's what's receiving the signals from space, from the constellation, from multiple satellites. Now, there's a cable connecting that to the box on the rod, connected to the rod. Now, what that is that's actually a data logger, and that's actually taking the measurements that the receiver is getting and actually calculating your location. So it's taking the time of arrival of all those different signals and calculating where you are relative to that constellation. So GPS is used extensively in navigation purposes, as I'm sure you're aware of, in terms of your car as well as your phone will use it, but it's also used extensively in construction purposes. In fact, even a few centimeters or up to a meter off at a construction site can spell disaster for an entire project or set you back months and millions of dollars by having to reset footings. So it's really important that you understand how the system works in order to accurately position yourself on the Earth so that you can save money and make your operations much smoother. Now, why not use surveying? Traditional surveying techniques such as the one you see here where they're using a total station, they're accurate, but they're much, much slower. So in this case, you have one person operating the survey equipment or the total station, one person out in the field roving around with a prism and rod. That signal from the total station is transmitted out, hits the prism, and is reflected back. Now, based on the geometry of that signal transmission and receiving, you can determine the location of that prism. However, this is much, much slower, especially if you're surveying a very large area. The advantage of GPS is that it's faster, significantly in fact. Instead of having two people doing this, you could have one person doing the same survey and it would take much less time. However, given just recreational systems, it tends to be less accurate. And that's why it says less accurate, but it's sometimes that qualifier is because if you have survey grade GPS equipment, it is possible to increase the accuracy of your GPS survey down to within centimeters or even millimeters, depending on the equipment you have and the time constraints and the budget constraints. The initial purpose of the GPS constellation was to track soldiers as well as weapons guidance. It's still used extensively today in military applications. You can see here an example where you have GPS built in actually to a mobile device. GPS is integrated in a lot a lot of different mobile devices, everything from computers to tablets to cell phones to entire vehicles, and including weapons. GPS is also used for navigation, so we'll get into it later on, where it's important that you understand very accurately and very precisely where you are, especially if you think of navigating into a harbor. So if you're navigating into a harbor, say at night, where you don't have that visibility, you need to know where those sand shoals, where those rocky outcrops are, where it gets shallower and deeper. And you need to know where you are relative to all those hazards. Well, using a traditional survey system wouldn't be appropriate. You need that real-time feedback. So in maritime navigation, there's actually differential GPS, which we'll cover later in the course, that's used extensively. You also find that there's a wide area augmentation system used for aviation navigation, and that's once again to improve the positioning of those planes in all aspects of the flight, everything from takeoff to approach to landing. GPS is also used in mapping bathymetry. So in order to very accurately and very precisely map the bathymetry of, say, a lake, it's important to understand more precisely and more accurately where you are on that lake. GNSS is also used in topographic mapping. So here you can see an example where we can see buildings, we can see trees even, we can see harbors, we can also see bridges. And so GNSS or GPS is needed to very precisely position the aircraft in this case. Now, the previous image, so this image as well as other images similar to it on the bottom right are produced using LiDAR. Now, what this is it's laser interferometry detection and ranging. It's also, you may hear it called light detection and ranging. It's basically a laser-based survey of the topography. And it can be done from anything from a fixed-wing aircraft to helicopters, or it can be even ground-based, where you may mount it on the back of a vehicle, or you carry it out and set it on a tripod and you survey the area. Now, in this case, you need a differential GPS system. The accuracy of the LiDAR system itself is millimeters to centimeters, depending on the system. And in order for that survey to be accurate, you need to know very, very precisely and accurately where you are on the Earth. So using a differential GPS or DGPS system in conjunction with ground control, or as a ground control, you can produce a topographic surface with a vertical accuracy up to or even better than 5 centimeters. Here we have an example of it along the coast. This is actually looking at North Padre Island or Padre Island National Seashore down just south of Corpus Christi. And so you can see we have a digital elevation model or DEM produced from a LiDAR survey. And you can see this is at a 1 meter resolution, so we were able to pull out very, very fine scale features on the dune. You can see that in the lower right where you can see we can pick out the dune, but we can also pick out even subtle variations in the elevation of the dune and features behind the dune as well. So this provides an improved data source that we can then track dune recovery and island evolution. It's also used as ground truthing for a variety of different purposes. In this case, it's a coastal system where we're ground truthing some measurement on a mud flat. It's also used in change detection monitoring. In this case, we're looking at a series of shorelines that have been surveyed using GNSS. So you can see the shoreline in 2005 was closer to the water. And then as we go through time, the shoreline or that cliff essentially just steps back and retreats back. Now, presumably in this case, that may be due to increased wave erosion. So the waves come up, they impact that bluff, and they erode it away, and they carry the sediment off. And through time, that's going to cause that cliff or that bluff to erode back. And so GNSS and GPS are really great ways to monitor this change and to track this change. It's also used extensively in geological monitoring. So here we have an example of electromagnetic induction. So it's a geophysical technique to measure the groundwater as well as the subsurface geology, and the two signals combined provides you a representative example of what's happening in the subsurface. You can see this system has a GPS built into it, integrated into it, and so when we're doing a survey across an area such as this is actually North Padre Island, or Padre Island National Seashore once again. These are actually a series, and if you zoom in really closely, these are a series of points. Each one has a geophysical measurement with it, which then we can interpret in a geological sense. Now, Trimble survey systems have also acquired a seismic geophone system, where now they sell a single system which has a geophone for seismic sensing and a GPS built in, all into a single portable system that you can take, set out in the field. It has its own battery life and everything, and all you have to do is collect the data and process it. So you can use not only EM, you can use ground penetrating radar, and you can use seismic systems, all with GPS or GNSS systems. It's also used for geological monitoring of volcanic activity and fault activity. So there's a series of stations, such as the one up in the upper left here, set up by the USGS and other agencies across the US and really around the world. And what these do is they monitor the vertical and horizontal displacements very, very precisely. So we're talking on the order of centimeters. And by measuring that displacement vertically and horizontally, we can get a better sense for how that magma plume is coming up closer to the Earth's surface. So as it gets closer to the Earth's surface, you'll get more crustal deformation, which means that you'll have more vertical and horizontal deformation or movement of that station. And so by tracking the rate at which it's moving horizontally and vertically across a series of stations across the single volcanic active zone, we can get a better sense for more accurately predicting and understanding how the subsurface is changing and when an eruption may occur. GPS is also used for tracking various different wildlife. It's used for tracking sea turtles as well as sharks as well as fish. Now, this used to be done using radio systems. The disadvantage there is that you had to get so close before you could even pick up the animal. That's a problem if you're dealing with an aquatic species that may not pop up that often. So using GPS, you can set the system to where it actually transmits a location signal that transmits or relays back down to the researcher, and you can very precisely track an animal through time. It's also used in animal surveys where you have these GPS collars. Now, the old way of doing this was, once again, with radio collars, where you had a radio antenna and you had to go out into the field and it was directional. So you would kind of hold it up and you'd kind of circle around, kind of wave it around, and if you picked up a signal, you knew that the animal was in that direction. But that's about all you could say. So you had some very crude understanding of where that animal was, not very precisely. Well, improvement in technology have allowed us to replace those radio collars with GPS collars, such as you see in the upper right here. And we can actually track everything from moose to elk to wolves to rattlesnakes, and we can very precisely track the animals and get a better understanding of how they're using their habitat, where they're moving, when they're moving there, and develop a more effective management strategy. This is also used for current monitoring. So here you can see it's called a drogue, where there's a dog collar GPS, there's a light, and there's a visual marker. And by putting these in the water, we could track the currents. Now, we have also used these extensively for rip current research, where you drop the drogue in a rip current. It goes out, is carried out away from the shore by the rip, and actually, in some instances, not all, but some instances, actually reattaches back down the coast further down. Now, that's not always the case, but that's another instance of where we've used GPS in these dog collars. We've mounted the dog collar GPS units on drogues and put them in the rips to track how the rips change and how fast they're flowing. So that's a little bit about the history of geodesy and GNSS. For next class, readings 2 and 3 on eCampus may be helpful. Hopefully you have a better understanding of how GNSS operates, what its applications are, and how we got to that point in the first place. So how early navigation occurred, what was solved first, latitude, longitude, how did we address each of those, and in what order. Next class, in the remainder of the course, we'll go into more detail about GNSS systems, both the GPS system as well as other non-GPS systems.